Okay, now welcome back to our topic 1, section 2, or the second part. The last parameter we want to talk about or emphasize is the alcohol as a reactant. Okay, the reactant of this transesterification for this whole biodiesel production, we use the ethanol or methanol as the reactant. I will elaborate slightly more on the following slides why these two are true. Because the reason or the rationale behind it, we try to use the smaller alcohols rather than bigger ones. Okay, because these smaller ones are volatile. Volatiles also means the boiling points are lower. Boiling points, this concept, possibly you can recap from the organic chemistry again. Okay. The test method here we use is gas chromatography. We commonly short it as GC. Okay, this picture here is roughly illustrate a very simple structure or the components schematics graph of the GC. To most of you, this might be the first time to hear about this GC concept. What is chromatography or what is gas chromatography? We need some of the background information or knowledge about it. Gas chromatography is one type of the chromatography. Chromatography actually consider I normally explain it as it's a separation method. Okay, basically it's whatever chromatography means separation. Separation are not separation of pure compound. Definitely several compounds or several components, they mix together, we want to separate them, right? That's why we call it separation. The chromatography typically have two phases. Okay, these two phases. One is called stationary phase, one is called mobile phase. What does it mean? Imagine, okay, this is something, the yellow part, they do not move. Okay, basically they are the surface of the tubular structure, like we normally call it column. Okay, so basically coating on the inner surface that they don't move, by right they should not move. That is what they call it stationary phase. Another phase we call the mobile phase, which is they can movable. Mobile literally means movable, right? They will move from one end to the other end. They can be the gas or can be the liquid. But for the gas chromatography, particularly this mobile phase means the gas. That's why gas chromatography, this name comes from. How it works, how it separates, right? Just imagine me, Dr. Wang. I want to have a race, basically to compete who run faster on the sports track. Okay, the sports track, the track itself, you can consider that part as your stationary phase, the yellow part. Okay, we need to step on it, run on top of it, right? Okay, that is stationary phase. You and me will run on the same day, same thing. We start, okay, let's be ready, start. Then we start to run. But some of you definitely will run much faster than me. Some of you may be similar as me, not as that fast, or even don't know who, might be even slower than me, it's possible. So by given a certain distance, for example, 100 meter, some of you will be run faster and then go faster and reach to the ending point much faster than I do. Okay, so by such running process, the faster running one will reach to the ending point. The time keeper, they will just, okay, this is somebody, they reach the point. The second, the fast one, the third fast one, they can be separated. That is how this chromatography means. The mobile phase you can just consider as the air or the water flow or something, basically maybe can help you to move on your favor side. Okay, basically help you to move out of this track. Okay, that is normally the example I will provide as my class, how this separation means. We are going to further slightly explain this chromatography, use the word. Okay, just now we use the example. The components means people, me and you, who run faster than one, right? The component means each compound or each components. They are going to separate according to something different. For example, you are faster, your legs are longer than mine, or you got better stamina, or your muscle is stronger. That is according to something. What is something? Stationary phase, okay, and mobile phase or something else. We talk them about one by one, okay. Stationary phase means what? Means the if I, okay, imagine I have a particular shoe. My shoe have a stronger interaction with the sports track. Basically, my shoe, particularly the sole was treated sticky to the track, for example. So each step I try to run is very difficult. I like to stay there rather than I move myself. So means high affinity, basically high interaction force, stronger sticky parts. So means what? Means that if I have the stronger interaction with the track on the ground, I surely will have the longer retention time. Retention time means I will stay with them for longer time. I don't want to move away at all. So the stronger interaction with this stationary phase, basically I love the stationary phase. I like to stick with the stationary phase. So I will stay inside the column, inside of this analytical instrument for a longer time. Comparatively, if I have another shoe or you have another shoe which is comparing with this sporting track, so basically they have the better bounce force, they have the very well designed, perfect design of sports shoe. You just touch on the ground, they will give you momentum, can move faster, for example. That will give you a faster run, basically lower retention time or shorter retention time. That called lower affinity to this stationary phase, you will get a shorter retention time. If you still follows this logic here, okay, now we talk about the stationary phase. Okay, the stationary phase is chemically say they are compounds. They can be polar, they can be non-polar, right? Now, polar stationary phase, which normally we call it normal phase. Okay, normal phase column, stationary phase, basically quite polar. If I am the compound, it's also quite polar. Means I polar compounds, right? Molecules, similar, alike, dissolve. You still remember that logic? It means I have the polar compounds, they definitely will show stronger or higher affinity, a stronger interaction phase. They like to stick to each other. They don't want to be separated. That's why the polar compounds definitely will stay inside of the polar stationary phase for a longer time. That also means their retention time will be longer. You can pause here for a while to try to digest this logic. Comparatively, the non-polar compounds will react with polar compounds less, and they will react with the non-polar stationary phase for longer. Means the stationary phase can be different. They can be polar, they can be non-polar. For those non-polar stationary phase, we commonly call it the reverse phase column. This is a very important concept, not only for this subject, for all the chromatography. Later time, you will going to get in touch. They still use this same concept: polar compound, polar column, or reverse phase column, or normal phase column. That is how it works. Quite abstract or quite wordy here. We try to give you some elaboration. For example, some compounds, here we can also use the components. Elute means flush out or wash out or run faster out, okay? They run at different rate. Some is faster, some is slower, right? Okay, the stronger affinity with the stationary phase, surely they will be slower. They stay inside for a longer time. And compound with stronger affinity with the mobile phase. Basically, they have the less interaction with stationary phase. They will run faster. They will come out faster. The peak or the signal on the detector, they will appear in a faster way. So you will see the elute order, say which one comes first, which one comes later. So which one comes first, which means the run fastest one, they come out first. They love to stay inside, don't want to come out from the column, or they keep running inside, they do not reach to any point that one. They have the longer retention time, they come out of the column later. Here is another page of information how we term it. There's some terminology. Chromatogram means what? Means a graph. Okay, I can just roughly draw. Basically, is this x-axis will be the time. As a minutes or some minutes, it will be quite conventional. Okay, this one is the typical of the graph. Quite likely there will be a plot of detection the signal. Basically, is something like, okay, I got one peak. Okay, I have another peak. Okay, I have another peak, something like that. Okay, I have three compound, for example. So this plot of this signal means this graph here is called chromatogram, or you can call it chromatography profile somehow. Some people call it, sometimes I also call it that way. It's okay, at least you understand what that means. This graph, it definitely will consist the peak, a peak or several peaks. Okay, the peak for different components. For example, what I draw here is 3 peaks. Okay, and each peak, they surely have some areas. Okay, you see these parts, areas. If we draw the baseline from here, they also have the area that can be calculated. I believe you learn from mathematics, can do the integration. Nowadays, we don't need to do the manual integration. The machine will do on our behalf, no worry, okay? So they have their peak, they have their error, they also have their retention time. Still just now, previous slides, we explained the retention time, right? So basically say this peak 1, this is time 1, for example, this is time 2, this is time 3, this time 1, 2, 3 is their retention time. Did you realize I draw this retention time not on the end, the beginning, not an end? Basically, I try to be at the center if the peak is symmetrical. So basically, is the peak maximum point. At that point of time, we call it the retention time. Why do we introduce this kind of concept? Because later time we need to keep repeating ourselves, need these terms to characterize our analysis result. Okay, here is an example. I draw in an ugly way. Here is a prettier way. So you know this retention time, the first peak, for example, that is the retention time. The T0 here is the solvents coming out. You don't have to frustrate it too much. Basically, when we do the injection in the machine, the solvent will be the first one to come out. They will give us an indication how fast the analysis could be. Or sometimes we call it dead time of the column. It's okay. It's not our real peak. One more term we need to know called resolution. Means separation need to have the resolution because we want to optimize our chromatogram. For example, this graph here, right? The first peak is here, the second peak is here. These are quite well separated. But if Imagine I just draw a comparison one. Okay, I have the first peak like this. I have the second peak like this. We know okay, maybe I need to use a different color for you to see clearer. Okay, my first peak is in the blue. Okay, okay. So this separation does not really separate them well because there is some overlapping, right? How should we quantify or how we characterize whether the separation is good or not? We use the resolution as our professional term. How do we calculate or how do we present it, for example? Okay, there is a formula. The retention times difference, basically retention time of the first peak and second peak, the difference, basically retention time B minus retention time of A, then divide by the width, basically how wide, okay, how wide of these two peaks. If the broader, basically the fatter the peak is, the separation will be more difficult. That's why the peak is sharper is better, right? So we do not want to just use the width plus together. We want to the half of the peak. For example, if the half of them, they can be better separated. That's good enough. We just rearrange this 0.5 to be on top of it. Then we can just rewrite our formula like this one. Not that scary. Don't be too intimidated, timid about this calculation. From this part, we know how we evaluate beta separation or the descent separation or is a very poor separation. For example, okay, I have a sample, we call it lemon oil. Inside got minimally two compounds. One compound called laminin. Okay, we have our laminin's retention time is blah 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 minutes, and they do also have the baseline width, basically how fat the peak is. Another compound, they call it a gamma terpinin. They also coming out at this retention time 9.54 minutes. We see actually not that bad. I mean, difference one coming out 1 minute later or 1.2 minutes later roughly. The other second peak coming out. Is it considered a good separation or not? If this peak width is 0.64 minutes, basically on the x-axis or the units is minutes, right? And then how good the resolution is it? We just use the previous page formula to calculate it. So we are going to use 2 times of this retention time difference in minutes. Then we divide by the width. Either we just half width or we just two times of the retention time difference. They are all the same. So we know this time for this particular case, the R resolution is 1.47 roughly there. Is it good or bad? Yeah, we know the R is 1.47. What does it mean? Okay, in practical way, normally the separation is considered good if the R is roughly 1.5. If the R is below 1.2, 1.2 here, it's considered separation not that nice anymore. So consider insufficient. So we now roughly know, okay, 1.5, 1.2, roughly we know what is called a good separation now. But in order to make this R to be higher or more than 1.5 or roughly no worse than 1.2, we want this retention times difference, the T1 minus T2, this kind of stuff, to be larger. It means this two peak to be further away, don't just next to each other, overlapping to each other. That will give us a better resolution. Another factor is the peak width, because how fat is the peak. We prefer the skinny one, the sharp one. Basically, it's Some of the graph you see is almost as one line, but otherwise just be sharp rather than this kind of fat one. Compare the fat one, the sharp one. Normally the sharp one will give us the better resolution. This fat one sometimes it called is a hump shape, this kind of stuff. So you know this is the direction we are going to see. We know we want a better resolution, but how we do it? Okay, there is commonly for gas chromatography, there are two parameters we consider. One is column characteristic. Basically says the column efficiency. What this means? What this means is a good column or poor column. Okay, I'm not going to elaborate this one because it's quite complex branch. There's a lot of technical details. I'll leave it to somebody else to explain you if you go to university, or maybe you don't touch this topic. Don't mind about it. So basically, if you are offered a good column, there are high chance they will have the better resolution. Okay. Another parameter we are going to talk about is this operation temperature, which we are going to manipulate in our laboratory soon. Or not that soon for the practical session, we are going to meet ourselves for this part. What this means? This means the temperature high or low will affect the resolution or even how fast the analysis time. Generally say, a higher temperature will make the ELUN, basically make the run be faster. The compounds will tend to come out faster. They are more excited molecule inside. And the mobile phase, the viscosity is lower. So that's why everything moves faster. Okay, sounds like a favorite way if we are really on the track to run it. But normally say this also lead to the lower retention. Basically, of course, run faster, the retention time will be shorter. That's called lower retention. On the other comparative aspect, the lower temperature will give us slightly, actually a better resolution. Okay, for the lower retention one, they have the better one. But for the longer elute time, basically whatever is sticky inside of the column for the longer time, they tend to have the broader peak, basically the fatter peak, or the hump shape of the peak. Their retention time much higher. I'll give you an example in the following page. Okay, so we know for this time a column temperature programming can help us. Actually, for the whoever is doing the QC or doing the analytical job, use the gas chromatography or use whatever chromatography, we will know this kind of programming will help us to solve the well-resolved the peak separation parts. They can shorten the analysis time because we do not want to spend days or weeks to analyze one or two samples. We can also try to use this method to make the peaks be sharper or narrower. For example, the first sample, first graph here, okay? Use the laser pointer for the clearer. If we use the isothermal programming, basically we don't change the temperature, just use the 45 degree. We analyze one compound. We see the 1, 2, 3, 4, 5 peaks, almost 28, 29 minutes, right? And the fixed one is very hump-like. If we just don't do the programming, we just do the isothermal peak, just increase the temperature. Instead of 145, we use 145. You can see the 145, okay, more compounds coming out. Basically, compound coming out faster. Even the compound 5 here, it can be sharper, but the first few, they overlapping more severe way. Right? So we know the effect if we just increase the temperature. If we program this temperature from 30 to 180, basically we control the oven temperature when increase how much, then you can say, oh, not bad. It's not only 8 peaks, even this one get 9 peaks. Basically, got more compound to be nicely to be elongated out. And the peaks, they do not overlapping that much. Basically, they are well separated. If we are going to collect them, it's possible, right? 1, 2, 3, 4, and most of them, the peaks, or all of these peaks, they are very sharp and symmetrical, which is very nice separation. This is what we do the optimization, try to achieve to. Now we know the gas chromatography background knowledge, the theory parts. We want to use it. Right now we just want to know it, right? Well, we want to know it, we want to use it for the identifying different compounds. For example, whether this sample contaminate with some things or not, such as food products or the tea, traditional medicine products, etc. Okay, how we do it? We use exactly testing method or testing conditions, such as we use the same column, we use the same of the programming temperature programming method. If some of the peaks they showed the same retention time, okay, retention time is a very key word, okay. If they show the same retention time, very likely, or in this subject, we can assume it's true, they are the same compound. This concept will be very useful if we are going to do some fingerprinting profiling for some complex samples. I will give you an example to elaborate what this means. Okay, here we have two GC chromatogram or GC profiles. I have sample 1, I have sample 2. Sample 1, I have 1, 2, 3, 4, 5 peaks. And sample 2, I have 2 peaks. If we compare these two samples, we will find out this green circle, first green circle, they have the same retention time. And the second one, they also have the same retention time. So from this point of view, we can conclude the sample 2, these two compounds can be found in sample 1. They are the same compounds of the same retention time. Basically, as long as their retention time they matching to each other, they are the same compounds. If we use this logic, we can identify compounds. For example, if I know what is compound of this second sample, this first peak is something, second peak is something, then I will know the first sample, they also contain these two compounds. For example, maybe it's alcohol, maybe it's aldehyde, maybe it's something. Yeah, you will know particularly that compound present in our sample. This is called qualitative analysis, basically identifying what are they. If we are going to do the quantitative analysis, basically how much, I know what is this compound, but I don't know how much inside, then how we do it. Then we are going to use the word peak area. You still remember the previous slides we talked about the peak area, right? The peak area will correlate to this content. What this means is, let's say this 3 graph here. If I have 1 molecule or 10 molecule, I have this peak area. If I have 9 molecule, it's slightly less, right? You see the error, it's slightly less, it's only 9. If I have 11 compounds, 11 molecules, I have even bigger the errors. So means what this concept is, this peak area is proportional to the analyzed content. Basically, how much is the content is can reflect by this peak area. If we get this idea, it means if I can just use the machine to analyze how big the error they give to me, I know how much analyzed insights already. That is how we are going to quantify our analyze. This sounds very good, but it also brings us another wonder. It means what? If I'm going to inject my sample, maybe my 1.0 microliter, my friends 1.0 microliter, we think we are doing the 1.0, but maybe it's not exactly some human error when we do our sample preparation. It still fluctuates. Basically, some human error or something, whatever factor, they affect our accuracy, right? Wow, that is means my test result may not be accurate, which worries some of us, or most of us, or even all of us. How are we going to handle this concern here? Okay, we have a way. Okay, this way we call it internal standard. The following several pages, we are going to explain what this means. Internal standard, basically we are going to put another compound inside our sample proportionally to our analyze. We still follow just now the logic. If we put 1.0, 0.9, 1.1 microliter, they give us the different peak area, right? But if we look into these two peaks correlation or the peak ratio, for example, okay, they are the same actually. Excuse me. So means no matter how we fluctuate the injection volume, the peak ratio, they remain the same. They remain the constant. That means even my hand may be shaking a little bit, I left a little bit in my syringe or something, I still can get my very accurate result. Then we can use the calibration curve to get our analytical result. The meaning is if I know I prepare a series of sample. I know my concentration will be 0, 10, 20, blah, blah, blah things. I have my 6 sample here. I can analyze my standard samples, basically my known sample. Standard sample means known sample. Okay, I made it so I know how much I put inside. I have the peak error ratio. So basically I have my analyzed sample inside. I have my internal standard inside. I have the peak error ratio. They can proportionally increase. So this curve, we can call it standard curve. Then I have another sample, use the same method. If I have my peak ratio analyzed as the result, then I can use this graph or use this plot to deduce back how much is my calculation. That is the concept. Don't worry, we are going to learn more about this part and practical parts. This technique, we call it internal standard. Internal standard on the y-axis, we always use the peak area ratio. Please focus on this part, okay? This is a very direct link to this part. Okay, the internal standard, we know the internal standard, internal something, but how we choose it commonly is another compound which is quite similar to the analyze we want to analyze. Such as if we are going to analyze ethanol, for in this case, we can use propanol or butanol. Propanol or butanol, basically carbon 3 or carbon 4 compared to carbon 2 ethanol, which is quite good internal standard we can use. This is a rough example. Okay, I took some of the data from the past year's experiment, or I did some about this part. So we know our ethanol concentration, this 1, 2, 5, 10 is what we made it. And we know this area of this ethanol. We also know our internal standard. In this case, we use the butanol. And with these values, I can use the ethanol one divided by the butanol one. That is the ratio, right? Peak area ratio. So I use this one divided by here, it will be here. So blah, blah, thing, I can just calculate all of this peak ratio. This is the experimental data, the first up to this row. Okay, now I also have one more sample. I don't know. I mean, standard, I know I made it. Unknown sample, I still can merit it. I also can merit it. I also can get my peak error ratio. If I use this data, this column and this column, these two columns, I plot it, use the Excel sheet. Okay, in case any of you, if you are not very sure how to use the Excel sheet, please approach to me. I can demo you. Okay, we can work together to learn together. Okay, if we plot this part together, we can have, I just put this table here. Okay, the graph will be look like this. And Excel sheet, the beauty part is they will automatically generate this function and R square to be here. R square here means how good the linearity of your graph is. Now closer to the 1, the better the linearity is. So with this function, okay, with this function here, if we know our samples y is 0.469, we can sub in and calculate that how much is our ethanol concentration. This is how we are going to do the data analysis or data process. This is also the method we are going to do in our laboratory when we do our practical one. We are going to learn it together at that point in time on hands-on session. Okay, now we intensively learn a lot about the GC plus the GC analysis for ethanol. Okay, I simplified a lot of the contents from some other videos. I hope you can take some time to understand more about this GC. Here is the YouTube links. I will going to post these links into our Brightspace as well. There is a much more detailed explanation about the GC. You can just skip those very technical part we are not covered. Surely you can find some of the explanation about the GC theory part, basically the structure, how it works. This topic we did not cover that part. I think that is the majority part for this analytical for ethanol as a reactant for this biodiesel production. Okay, we have a quick summary, brief summary of what we learned for this topic 1 chemical analysis. First, we introduced several concepts like the biodiesel, what is the waste cook oil, and what's the problem with the waste cook oil. We directly use it for trans-esterification. And trans-esterification, this reaction, I think this is the only place we are going to really explain you how the reaction goes or what this means. Following point, we introduced a few important parameters to analyze. Just bear in mind, this is not full panel parameters we need to analyze. If you are going to continue your career on this industry, I believe you will see much more. Surely it's realistic. Okay, and we do emphasize a lot on these chemical analysis technologies, which we emphasize a lot on the acid number, free fatty acid determinations. We do briefly introduce you the water content, use the machine colorimetric method to analyze it, but we really did not really elaborate it. We do emphasize a lot use the GC gas chromatography to detect the concentration about the ethanol. We do hope you or we do require you to understand this ethanol's analytical technology and know some of the brief way about this gas chromatography. That is all for this topic 1 chemical analysis of the PPRE subjects. I also attach just very briefly two reference where I get some of the information or some of the context from. Even this second one is you still remember the table I briefed you some of the standards, European nation and American area that standard. I took that table from this reference. Okay, that's all I have for you for this subject. All the best for the rest. Thank you very much.